The speed by surface operator shares a lot of its functionality with the basic speed operator. Its main difference is that it uses the normal direction of a surface to derive the particle's orientation. Generally, you would want to use a speed by surface operator in conjunction with a position object operator. The position object operator places the particles on the object's surface, and then the speed by surface operator picks up the normal direction closest to the particle and uses that for its direction of travel. Another benefit of the speed by surface operator is to offer control of the speed assigned to each particle via a texture on the object. You can choose which material ID the speed control is based on, plus how the bitmap is used to derive the speed and direction. So you have a lot of control. So we'll quickly run through the parameters, and then we'll actually have a look at how they work in action. So the first option we have is, do we set the speed once, or do we control it continuously? So that's something we'll come to later. Setting speed once, as you can imagine, actually does it once when the particle enters the operator, and controlling speed continuously applies the speed modification continuously throughout the duration that the particle is in this event. The speed value is assigned here, and you can either assign a straightforward value, as you can see here I've got 5, or you can add some variation to it using the variation parameter. Then you've got surface geometry, and this is the usual list box, and you can assign as many pieces of geometry as you want. As you can see in this case, I've actually assigned this geosphere here, geosphere 1, and you've got the usual options for adding geometry, adding a list of geometry, or removing geometry. If the geometry animates over time, then you need to turn on this tick box, and that will actually update the way it affects the speed of your particles over time. Subframe sampling. This is useful when the set speed once is active. This is only available then. And what it does is it allows you to assign the initial speed value here based on the shape of the mesh on a subframe basis, rather than just being on a frame by frame basis. And this will give you slightly more accurate speed and direction assignments. You have speed by material, and when this is active, you can see you have a number of options. We'll just put it to grayscale multiplier for now, turn that back off again. When it's active as well, you've got use submaterial ID, as I just mentioned, so you can actually use a submaterial rather than the main material as the material to use here. Then you have the direction flyout, and you can see at the moment it's set to surface normals. The other options are out of surface and parallel to surface. You can also use a divergence value to vary away from that actual assignment slightly to vary the direction. Then you have continuous speed control, and this only actually becomes active when you have control speed continuous turned on. When this is active, these values here allow you to actually assign how much control the mesh surface has over the speed of your particles. You can see you've got acceleration limit. You can have a limited or an unlimited range. You can see there it's unlimited. If it's limited, then you've got these two ranges here, the full effect range in units and the fall off zone in units. And then if you animate any of the parameters, you've got animation offset keying. So you've got the usual options here: absolute time, particle age, and event duration. And finally we have the usual uniqueness parameters here. Now if we actually look at our event and we see how it's built up, then it'll help us to understand a little bit more clearly what's going on here. We can see that our particles have been born on frame 0, and we've got 50 of them, and we're using subframe sampling. Then you can see we're positioning our particles based on an object, and again I'm using this geosphere. So the particles are then positioned all over the surface of the geosphere. Then I have a shape instance, and this assigns a cylindrical shape to our particles, which makes it easier to actually see which direction they're traveling in. Then we actually have our speed by surface operator, and then we have a rotation operator set to speed space follow, and that basically aligns our particles along the direction of travel. So that again, that gives us an insight into the actual orientation of the particle. And then we're just displaying the geometry as the particles as geometry here. You can see I've used a bright yellow color to make it clear. So if we go to our speed by surface operator, you can see it's currently on control speed continuously. I'll change that to set speed once. And the main parameters that you'll use in this operator are the how often the speed is assigned. You can see I've set it to set speed once, and the direction. They're the main parameters that you'll be using. And then these other parameters here are basically to fine-tune the control of that. So at the moment, the direction that we're assigning to our particles is based on the surface normals. Now, because it's based on the surface normals, that means that the direction of travel will always be facing out from the surface. As you can see, all the particles here are facing out from the surface. Now, the actual speed assignment will also be positive away from the surface as well. So if I scrub through the timeline, I'll just press play. You can see our particles are flying outwards. So that's pretty easy to understand what's going on there. Now, if I go back and I change the option to out of surface, the direction is the same as before, but now the actual direction can be modified. The speed can be, a negative value, and that can be based on the position of the particle in relation to the surface. Now, it may not be obvious, but some of our particles are actually marginally inside the surface, and some of them are marginally outside the surface. So that means that some of our particles will actually fly outwards from the surface, and some of them will fly inwards. So if I press play, you can see this in action. Some of the particles are flying in towards the center of our sphere, then they're converging, and then they're just flying back out again. So you can see you've got two different options there which can be used for two different circumstances. The final option is parallel to surface. I'll go back to the beginning and press play. Now you can see the direction, the orientation of the particles, and the actual speed is now being assigned parallel to the face closest to the actual particle. So if I press play, you can see the particles fly off based on that orientation and speed. Now, because I've got set speed once, this is a one-time assignment of speed and direction. So you can see the particles are just flying outwards. So if we go back and we say surface normals, and we set the speed to continuous and press play, you can see we're not really getting any difference in our end result. That's because the actual surface normals of the surface, they're not varying at all. There's no animation on them, there's no distortion of the surface, so effectively our particles can carry on flying along the original vector that they were given. So to show that it actually does have an effect, and you can see that when we actually activate control speed continuously, the actual control speed continuous controls come into action. And you can see I've given them quite a big range here. Minimum range of 10, maximum range of 50. So if I select the sphere, you can see I've got a noise modifier here applied. I'll turn that on. And now this is actually set up to animate. It'll distort the sphere over time. And we've got continuous control of the particles based on the surface normal. So if we press play, you can see now that as the particles fly outwards, they're not actually being affected by the surface. Now, the reason for that is that we actually have to activate animated shape for this to actually take effect. So let's go back to the beginning. We'll turn on animated shape, and we'll press play again. And now the actual animated shape of the surface is being sampled from integration step to integration step. And you can see that our particles are looking at the surface nearest to them, and they're using the normal at the point on that surface to actually determine their orientation and speed. Now, this is producing slightly flickery results, and that's because the particles are looking for the closest point on the surface nearest to them. And because we've got quite a large deformation going on here in the mesh, that means that at any one point, the closest point on the surface could actually switch to another point. And that does actually happen during the animation. And that causes some of the particles to actually flicker and pop their orientation. So you can see that on some of the particles, they're actually popping their orientation here and there. So that's something to be aware of. Just rewind back to the beginning. This works basically the same with out of surface. We'll play that as well. And you can see the orientation has been modified, and it's having quite a big effect actually on the particles inside the surface. You can see they actually can't get out because they're being assigned different speeds all the time. So you can see you've got some quite interesting results with that. And then if we go to parallel to surface and we press play, you can see that our particle speed and orientation is actually based on the surface. And because the surface is flexing and switching and morphing around so much, our particles get very, very confused by what's actually happening here. So if we go back to the beginning and we turn off the noise modifier, what you'll actually see now is that the